Yeah, yeah.
Great,
All right,
thanks.
everyone, we're already a minute late, so let's please try to get started right now. So yeah, we'll just go through some of the brief preamble stuff very quickly, since I'm sure you've seen it before by now. Um, this is a session about science synergies with Rubin, Roman, and Euclid, also with emphasis on joint data processing. So as a reminder, we have this code of conduct that we need to abide by at all times. We also have some stuff at play involving COVID. I think you may have seen an email about that from Rand Powell earlier today. Different people have different comfort levels with that. Wear a mask if you would like. And then here's some stuff about how you can monitor the participation in different rooms in person. And lastly, let's just be mindful that we have virtual participants, so let's try to always speak into a mic and so forth so that everyone can follow along wherever they are. All right, so here's the agenda for this session. I'll start out with 10 to 15 minutes just talking about, in broad terms, Rubin, Roman, Euclid complementarity and synergies. Then we'll have 15 minutes dedicated to Euclid-Rubin Synergy, 30 minutes dedicated to Roman-Rubin Synergy, and then lastly, 30 minutes dedicated to simulations and data access topics. Okay, so to start out with my portion, just giving a broad overview so we're all on the same page about Rubin, Roman, Euclid complementarity. Here's an adaptation of a figure I saw Jelko present many years ago, and it always stuck with me. It's kind of just a way of illustrating the different strengths and complementarity of the different surveys. So the way you can think about this is that each of the three surveys tends to really excel in two of these axes, being depth, PSF, and area, so three axes in total. PSF meaning angular resolution, so Euclid and Roman excel there because they're in space and they can get kind of Hubble-like or near-Hubble-like resolution. Area is where Euclid, its wide survey, and Rubin LSST survey excel, a substantial fraction of the sky, a third to a half of it. And then depth is where Roman and Rubin really excel, going about 2 mags deeper than Euclid. And you can see some of the various parameters here of the different surveys pulled from different resources online. I won't go through and read every single number on here in the interest of time, but there are also additional complementaries that aren't captured in this diagram. For example, wavelengths. So Rubin is optical, red optical, but you can add in infrared by bringing in Roman and Euclid. There's also imaging plus spectroscopy. So both Roman and Euclid have spectroscopic capabilities, whereas Rubin does not. And then time baseline, of course, Rubin LSST has a super unique aspect where it's very wide area, but also extremely high coverage in terms of revisits to every sky location in the survey. By now, there have been many different studies and white papers and reports that have all uniformly found that it's going to be extremely important and impactful scientifically in order to combine and maximize the combined value of these data sets together. So cross-survey science synergies range from cosmology to virtually all areas of astronomy. Cosmology has been particularly well studied. For example, this Rhodes et al. Tri-agency report across DOE, NASA, and NSF. But more generally, across all of astrophysics, there was this Cherry et al. 2019 Joint Survey Processing Report, and more recently, the Aura Roman Rubin Synergies Working Group R2D2, sometimes it's called report. And here's an example from the non-cosmology area of what you can do by sort of mapping the whole galactic plane. If you were able to combine deep data from, say, Roman and Rubin in the plane, you could essentially see through the dust across all of the Milky Way and make a better 3D dust map than ever before. So now I'm just going to give an overview of some of the basic parameters we're working with. Generally, I'll focus on the widest area parts of these surveys from each mission, and also, what their wavelength coverage is and sky area coverage is and so forth. So here's the Euclid, what's called the wide survey, which is about 15,000 square degrees. So it's kind of trying to do all the sky except leaving out the galactic and ecliptic planes. Visible light imaging to 24.5 AB, and then similarly deep, although not quite as deep, in the near infrared, plus Grism spectroscopy in the near infrared with a resolution of several hundred. And in terms of timeline, you can see here, of course, Euclid, what's great about it right now is that it's already launched, it's already got data, and in fact, it's already released some of the data in what's called its ERO, or early release observations. And you can see more of the full timeline here for its data releases. Roman is scheduled for launch in October 2026, assuming things go to plan. The area is dominated by what's called the High Latitude Wide Area Survey, with that acronym for short. And that is YJH imaging to about 27 mag AB plus 1 to 2 micron slitless spectroscopy with a resolution of several hundred. Interestingly, Roman has recently approved an early definition galactic plane survey that could add a significant amount of area. And so that's what the orange is in this diagram. I've sort of just drawn something totally that I personally made up because it hasn't been defined yet exactly how much area or what filters, what cadence, et cetera, will be in there. And of course, there's also some other core community surveys from Roman, the High Latitude Time Domain Survey and the Galactic Bulge Time Domain Survey, although I won't focus so much on those because they're a very small area, although they do have high cadence. And Roman has some very strict mission requirements, basically saying that within a week of data being taken, virtually all of the data needs to be reduced and made publicly available, and then that all data must be made publicly available within 6 months of acquisition. Okay, so this is the Rubin Community Workshop, so now onto Rubin and LSST. So we're expecting the LSST survey to start in, let's say, mid-2025. I'll show a little bit more detail on that in the next slide. It's anticipated to be a 10-year survey, so 2025 to 2035. 6 bands, UGRIZY, covering 0.3 to 1 plus microns. The footprint cadence are still being finalized and optimized. Roughly speaking, about 800 visits per sky location is the time domain aspect here across the whole footprint, the whole wide, fast, deep footprint. And of course, this is a ground-based survey, unlike the other two. And so you're going to get the whole sky as visible from Cerro Pachon, or at least going as far north as seems reasonable given air mass constraints. And then you have a total of close to 20,000 square degrees is currently in the baseline plan, I believe. So here's the latest, greatest timeline for early science with LSST and Rubin. I won't read it in full detail, but this latest, greatest version will shortly be updated to Rubin Tech Note 011, which is where you should generally check for updates or the latest on the Rubin LSST timeline and schedule. Just to, again, set the context, set the stage, here's what the different band passes look like in Rubin and Euclid first. So this is only showing the imaging capabilities, but nevertheless, you can see Rubin's 6 bands. There's this broad visible filter that Euclid brings in, plus it has 3 Y, J, and H filters that cover roughly 1 to 2 microns. And here's a similar comparison for Roman. In this case, it does also include the GRISM and PRISM for spectroscopy. And you can see that Roman extends out to actually 2+ microns now, thanks to the recent addition of the F213 filter, which again would be great for extending the wavelength coverage that LSST could provide. Here's a figure you may have seen before. It's a little bit of a classic figure by now, but showing the different depths in more detail of each of these 3 surveys band by band. So again, just a little bit of extra added detail here. And what it shows is, as we mentioned before, Rubin and Roman are pretty well matched as far as depth, roughly depth of 27 AB. Euclid is about a couple mags shallower than that. But of course, the nice thing with Euclid is that it's getting data right now. So a little bit more about the comparison to these 3 surveys. So there will be this sort of special sky region in the southern extragalactic sky that will have roughly 2,000 square degrees, where the high latitude wide area survey from Roman overlaps with both the wide, fast, deep survey from Rubin and also the Euclid wide survey. So that's going to be a really special and highly studied area. But then there's also other overlaps. So Rubin plus Euclid, it just shares the exact same overlap I talked about in this southern sky region. Roman and Rubin have, again, the same high latitude wide area survey, 2,000 square degrees, but there's also a little bit of a new wrinkle here, which is that if any of this new early definition Roman galactic plane survey is in the southern sky, then that could lead to a significant amount of interesting and very different overlap as far as crowded fields between Roman and Rubin. And then with Rubin plus Euclid, you get about 7,000 square degrees in the southern extragalactic sky, mainly defined by the deck limit of Rubin plus the galactic and ecliptic latitude cuts that Euclid makes. So here is showing in the red the special 2,000 square degree sky area where you have overlap of all 3. Yeah, so this is my last slide about maximizing the combined science. There's many different ways that you could think about going about doing this. You could coordinate along different aspects of the projects, right? You could try to coordinate the footprint, you could try to coordinate the cadence, you could try to coordinate simulations among different collaborations. But the one we're going to focus on mostly today is the idea of joint data processing. And there's different flavors within joint data processing. One relatively simple one you could imagine, although I'm sure it's harder in practice to do, is just being able to let people easily cross-match catalogs. A perhaps more interesting and more challenging one, technically and resource-wise, is what's called force photometry, which has been done successfully in other examples, like through the DESI project, where we combined DCAM data in the optical with much higher resolution than WISE. And as you can see in the bottom scatter plots here, that allows you to pull out a lot of meaningful and valuable information from the lower resolution survey that you simply could not do from catalog cross-matching if you would analyze the survey separately. And so this is one of the emphasis of this session, and the broader effort here is to try to understand how do we make these types of things happen for these next generation surveys, coordinating as necessary across missions and getting necessary resources to be able to do all of this hard work. So thank you, I'll leave it at that. We could do a couple questions. We do have a packed agenda, so I'm also happy to not do questions. Okay, so I think we'll plan to just move straight on to James. I want to give James the... Yeah, so our next speaker is James Colbert, who's going to be telling us about the Rubin Euclid Derived Data Products Implementation Working Group.
All right, yeah, so I'm here to tell you about the Derived Data Products Implementation Working Group. So I'll give you a little intro, then I'll tell you about what we've been up to, and then I'll try to give you a little picture of where we're headed. All right, so the context. So before the implementation group, there was the Derived Data Products Working Group. That was basically some Rubin and Euclid management appointed in 2020, about 13 scientists to each side of the group, a Rubin, 13 Euclid scientists. And basically with the idea of producing jointly derived data products constructed from the combination of Rubin and Euclid data. And everyone saw this, that there was potential here to open up new discovery space beyond that of what each mission could achieve independently. So people were very excited about that's what this group looked into. It was basically headed up by Leanne and John Charles. They produced a report, an initial recommendations report, back at the very end of 2021. You can go and get it off the archive. Basically, if you just type in like Guy et al. GDP, and you can find it pretty quickly. That's how I always get it over and over again. And basically, it was an 80-ish page report. There was 120 co-authors. Essentially, it was a lot of people helped contribute to it. First 14 pages give an overview, and then there are 10 independent science sections. And talk about survey optimization, and there's even a one-page executive summary if you really just want to glance at it real quickly. But there was emphasis made to have all the interested Rubin and Euclid data rights holders to contribute via online discussion forum. And that's, I'll actually talk about this forum a little more again. What was in the report, basically it identified 63 different derived data products with 5 key aspects of each. The science case for it, the nature of the product, the algorithms that would need to be, the computing that would be required to make it, and the time scale that they thought you might be able to produce these products. Covered 10 different products. Cross-cutting, which means cross-cutting as all different types of science, products that would be useful for multiple science cases. And then, solar system, local volume, galactic plane, local universe, transients, galaxy evolution, AGN, static cosmology, strong lensing, and primeval universe. So nearly everything you could want. I'm sure somebody has something we've missed, but that was all included in the report. The 5 prime products, so I'll talk about a couple more times as we go along. These cross-cutting products, they're mostly just photometry catalogs. They're listed here at the bottom. They're basically come in like 3 different levels of complexity, starting with sort of a basic list driven and then getting into more and more joint pixel processing. Then there's an effort to make sort of pixel level photometric redshifts, and then there's image cutouts and stamps. We'll come back to this some more. Okay, So that was the former working group. Now we have the implementation working group of people that have been assigned to try to actually have these products come to life. Euclid-Rubin management appointed us back in December of last year. Basically, there's 14 of us. We formed the implementation drive data products working group. It's basically co-led by me, James Colbert, and Todd Lauer there. And then a bunch of other people. I'm not going to list everyone's here, but you see a lot of names, especially on the Rubin side, as they're here today. A lot of them are here today. And Jim Chang and Aaron. All right, what was our charges? Well, we're supposed to establish a roadmap for the creation of all these data products and explicitly identify which data products can and should be created immediately or quickly, might be a better word. Identify what technical capabilities individuals will need to have developed, will need to have to develop these products, and when possible, to identify which candidates with those capabilities and skills exist and get them involved. We need to identify what infrastructure requirements there are for the creation of these products. We need to identify which bodies and organizations might financially support the creation of the DPs. This is a big one. Just to be clear, at the moment, this group doesn't have any funding. We're not passing out any funding. We don't have funding to give anyone. We have to figure out where it's going to come from. That's what we're doing. And finally, we're going to deliver a roadmap to the Rubin and Euclid leadership, and then continue to update them along the way of what we're doing. All right, so we have regular meetings. We meet every 2 weeks. There are minutes from these meetings. You can actually go to the community forum website that we have. Any members of the astronomical community are welcome to register and participate and submit questions, whatever. To join the site automatically, there's a code, there's a password code, which I greater than some of its parts, all is one word. But if for some reason you lose this or whatever, email me, email Todd, just ask, we'll get you into the forum. But you can sort of do it automatically, password. Anyway, we release the meeting notes on a best effort basis. We don't do it like live. We actually produce the meeting notes, then we give people time to review to make sure that they didn't say that the notes don't say something they disagree with. But we do release them. The latest ones right now are about 2 months old. But in 2 weeks, it'll be 2 weeks. We're about 2 months. They basically release about 2 months behind what we're actually saying. And we do have regular outside contributors on various topics to the talks. We have people come in. We need to know something. We need to know about how Euclid is photometric catalog pipeline is working. We'll invite people and they'll come in and we'll talk. All right, so overarching context of the discussions, we have sort of two big guiding things that will often dominate. We talk about the protection of the key science with proprietary data. Both Rubin and Euclid data is proprietary. So the things we try to protect is Rubin's depth and Euclid's spatial resolution and infrared data. There's also an issue with the retention of Euclid's PSF models until they're publicly released, although that will presumably happen in data release 1. So it's not really much of an issue. Coming later. But while we're worried about the proprietary, we want to make sure that we are collaborating to get the best out of the two data sets. We want to some of the primary things that are driving us. We want to improve those photometric redshifts, both Euclid and Rubin, to the deeper Rubin optical photometry and the deep Euclid photometry. We want to use deblended photometry using the pixel level access to both data sets. So I'm just going to describe a couple of the other things that the group has been up to. We distributed a community survey back in April, May, sort of. So while we know most of the major joint processing players, we wanted to make sure that we were not missing or excluding any potential collaborators. So the goal of the survey was to allow the working group to coordinate with the different groups that are producing these products as an important component of our developing roadmap. So anyway, this community survey was distributed in a bunch of ways. It's just some of the initial, we got 34 responses to it. If you feel that you just the first you've heard about it and you want to contribute to it, just let us know. Just communicate with us. But I mean, this is sort of the example, the cross section of the sort of 34 people that about half of them were individuals, half were groups. Half the people that talk to us have access to both data sets already. We also have a simulation group. We talk about simulations. Actually, I'm a little short on time, so I'm going to leave simulations to other people to talk about, but we are concerned about making sure that simulations exist. All right, so we have the primary cross-cutting products. These are the photometry catalogs. I would say these are sort of the primary products that we're looking into. The general trend is you go from products, basically we call them DDP1, DDP2, DDP3. They increase in accuracy and decrease in the impact of contamination and confusion as you go from 1 to 3. They increase in complexity. They increase in the need for resources to make them. And they also increase in the delivery time to community, so you get to the community. There's a potential of a decrease in proprietary restrictions as we go along, but this last point is more under debate. But it's possible that as we get to these higher level products, we'll be able to have less restrictions. You'll be able to see more of the data, but that's a whole discussion I don't have time to get into either. All right, so again, we're still assembling the high level roadmaps. The details are still fluid and under debate, but basically DDP1, the basic idea is these are going to be, you're going to take output lists from each survey and you're going to feed it into the photometry measurement software of the other survey. And you're basically going to do a aperture photometry. It'll be an aperture which is scaled and probably it'll know the shape of the object, so it won't be like just a simple circular aperture, but it'll just be aperture photometry. Then the more complex one, DDP2, has joint photometry catalogs creating all the available pixels together with the goal of producing products that are most compatible with the analysis already planned or ongoing with the other surveys. So the intention here is to use the already developed software that exists. So for instance, T-Photo for Euclid, using the Rubin to Blender. We're gonna, again, feed the coordinates found from one survey to the other one, but now we need access to most pixel sets so we can run the software that already exists. And this is really important, for instance, for Euclid. This is going to produce the product that they can directly compare with what they're already doing. They already have other data sets that they are combining together. So this is the data set that gives them that. And finally, DDP3, joint pixel catalogs will be created using all the available pixels together for both for source detection and photometry track. This is sort of like, we just want to do it the best way possible. Data, bring it to one spot and produce the best catalog we can. This is my last slide. I just want to kind of put some time, because a lot of people have these questions like, when is this going to happen? So at the top of the slide, I just sort of give you things I know are going to happen. And that's right now we're going to deliver our roadmap by the end of the summer. The ones in red have nothing to do with our group. They're just major milestones that are happening in these two missions. March 2025, Euclid is going to get its DR1 internal release. It's data release 1, internal release. Fall 2025, Rubin starts its main survey. March 26th is the public Euclid DR1. That's when the entire world will see what's in Euclid. Fall 2026, that's Rubin DR1, basically. And in between, around the same time, we're going to, maybe a little before the Rubin DR1, we're hoping to have our final report. Delivery date, preliminary, if you just want some idea, when you want my first guess, which is really what this is to when these things might come to exist. And again, this is subject to change, and anything I say would have to undergo project approval. I'm not the final word on this. DDP1 and DDP5, probably early 2026. DDP2, late 2026. DDP3, now, and the farther we get on this list, the more I'm making stuff up. But maybe late 2027, DDP4, 2028, off those 5 costs. That's it. We have time for questions, or should we just go to the next person?
So should we think of this whole effort as a NASA sponsored or NASA endorsed effort, or it's related to the question you made the point that there's sort of no funding to do all of this, and I sort of wanted to put that statement into a bit of
I mean,
context.
one of the sources of funding we are looking at is NASA funding, but I would not say this is a NASA sponsored effort. NASA's put a lot of effort, resources into some of the Rubin Roman stuff. Anything with Roman, NASA is definitely behind. This is definitely where the project's heads of Euclid and Rubin got together and said, we have to be able to share our data because there's so much we can.
Sorry if you said that and I missed it, but who will have access to the derived data products? Everybody who has data rights on either survey, or just the people who are in the crossover, or or everybody in the world?
So everyone has Rubin data. Everyone in both consortiums will have access to these data products. There will be, for some of the photometry catalogs, for instance, there'll be like two sets of there'll be two versions of DDP1 and I believe two versions of DDP2. One where you've used Rubin sources and got Euclid photometry and vice versa. So you only will, if you're Rubin, and you don't have Euclid data rights, then you only have access to the one where you Rubin sources and went and got Euclid photometry of those sources and vice versa. There's a whole complex, which I don't have time to get into, but there's a system of trying to protect the depths of the surveys. There's a system of not delivering things where you haven't detected sources, or you haven't detected things that you will have like matched depths for upper limits when we produce those, things like that too. You're not going to get the full power, at least in those earlier products. We're hoping by the time we get to the DDP3 product that we can sort of unleash the full power of the two surveys together, but we have to balance these proprietary issues.
So at some point, it might be that they will be publicly released to everybody? Or?
Well, I think it'll eventually be publicly released to everybody. That has not been officially announced, but once both surveys have been publicly released, and it would make sense that at least within some time period, they would eventually be public, yes.
Thanks, James. This is Bob Blum, Rubin Operations Director. This is a great summary of where we're at. And I hope people get the point here that we're trying to really provide more science than either survey could do on its own. And this is something that I think will happen eventually. I just wanted to point out that independent of anything that you have talked about here today, we also have agreed with the Euclid folks to share the data in the Deep Field South,
Yes.
the Euclid Deep Field South.
I'm trying to stick that in.
Sure.
Yes.
So that's coming soon or sooner, and it will be available. And in fact, it could probably help motivate and further develop a lot of the things that you've been talking about here today.
If people aren't familiar with Euclid, there's actually a quick look survey which will be released to the public by March of next year, which is, it's only a single pass, it's not deep, but it's over the deep fields. That we'll definitely be using that data and looking at how we can combine it with Rubin, an early data set.
Okay, so the next 30 minutes will focus on the Roman-Rubin synergy. I will start off by giving a brief description of the core community surveys and how we are defining those surveys. And then we'll hear from three core community survey science examples. One from the high latitude wide area survey, high latitude time domain survey, and the galactic bulge survey. And then at the end, Keith Bechtol and I will give a brief summary update on the actual status of the survey definition process that are going on currently. Okay, so Roman is a 5-year mission, and the vast majority of the observing time, at least at the very beginning, will focus on 3 large community surveys shown here. The 2 on the left, the high latitude wide area survey and the high latitude time domain survey, focus on cosmology, weak lensing in the wide area, and supernova type 1a supernova cosmology in the time domain survey, as well as the third one, the galactic bulge time domain survey, which will focus on exoplanets. So that will consist of roughly 75% of the observing time. The remaining 25% of the observing time will be selected from smaller general astrophysics surveys that people can write proposals and propose to do. All of the data will become public immediately, as Aaron said earlier. This is a different projection of what we saw earlier. Okay, that's fine. So the area in the galactic south, that's where the wide area survey will do a multi-band imaging survey of about 2,000 square degrees to measure shapes of galaxies and photometric redshifts. Smaller areas in blue and green will have a time domain component. The high latitude time domain survey will focus on type 1a supernova cosmology. It will have a cadence of about 5 days, maybe 10 days, depending on how the definition process pans out. The galactic bulge survey will have a higher cadence of about 15 minutes with a shorter period focused on a smaller area. The goal of the core community survey definition process is to accomplish the cosmology and exoplanet science goals, but also get input from the community so that we can design a survey that is also useful for many other things. And so what we did was we solicited input from the general community in terms of white papers and science pitches. 3 committees were constructed, 1 for each core community survey. And the committee members are reading or have read all of the science pitches and the white surveys, and are in the process of trying to incorporate the suggestions that were made in putting together an observing strategy that will, again, accomplish the cosmology and exoplanet science goals, but also produce other useful ancillary science. There will be no survey team selected for any of these core community surveys. It is really for the community. And as the data are going to be public right away, anyone can get access and do their science. So this is the timeline. Currently, we are in the process of reading and ingesting and incorporating the suggestions, coming up with observing strategies that incorporate many of the suggestions. And in the next, sorry, I'm flipping through slides. In the next several months, we will make recommendations to the time allocation committee. And the time allocation committee will actually decide on which of the surveys get what observing time, and coming up with a detailed plan that can accomplish everything in the 5-year survey. So here are some links, and let's move on to some of the science cases, interesting science cases that we can work on. So who's going first, Leanne?
Hello, can everyone hear me? Can you hear me? No?
Hear you.
You can hear me. Okay, good. Sorry about that. Okay, so I have to actually go to the next slide. Great, thank you. So I'm giving this slide on behalf of Federica Bianco. She was the lead author in a paper that a number of us from the Rubin Project Science team submitted to this core community survey call. The paper here is Bianco et al. I was part of this, so were several of the members of the PST. Essentially what we're proposing in this is a single band LSST matched depth survey over the footprint of the LSST wide fast deep. We propose this to be in just one filter. So filter 146, F146 filter to a depth of about 25 was what we found to be optimal. Whilst it would be very nice to do a multi-epoch, multi-filter full sky Roman survey, this would take far too long. We estimate that to cover the LSST wide fast deep footprint in just one filter would probably take about 4 months. But still, this would be a very useful, sort of simple, affordable in terms of observing time, general purpose survey that could serve a large number of science goals. Some of the highlights of this I've listed here. So if you essentially with this filter, you'll extend the wavelength coverage from Rubin's optical through into the near infrared wavelengths. And this will have benefit for both surveys. In Rubin science, this will bring in an extension of the wavelength range and increase spatial resolution. With the Roman science, it will bring in the time domain dimension and sort of shorter wavelength photometry that you get as well. So the Roman's spatial resolution and astrometric accuracy will be very advantageous for characterizing Rubin images. Rubin's multi-filter, temporally rich information complements Roman sky survey. And in addition, such a general purpose sort of survey could also support many other surveys and science goals. Everything from, I've just listed some here, photo Z, deblending, crowded field photometry, etc. And just here on the right, you see a picture here of a study that was done that shows as you add in the Roman filter, the near infrared, and the improvements that you see in photometric redshifts. So if you want to find out any more about this, the paper's here, it's on the archive. Please have a look and feel free to ask any questions. Thank you.
Hi, I'm going to speak briefly about the high latitude time domain survey. What do I do with this? Yeah, I can only count so high. Yeah. I'm just a figurehead, pretty face here, representing work done by many other people, developing the high latitude time domain survey. So this is explicitly for type 1a cosmology. You could be an optimist and say it's for supernova cosmology more generally, but I'm a simple person. And the current plan is to do a wide and deep tier, and there are active investigations to figure out exactly how wide that should be. If that's 10 square degrees, 20 square degrees, deep is probably 4, 5 square degrees. Here's an example of how you might do that coverage, like the detailed work by people like David Rubin, Ben Rose, Rebecca Hounsel, is like, how exactly would you use the time? What are the overheads of doing that? The wide is going a little lower in redshift. And so it's focusing on the bluest 4 filters. The deep is trying to go a little deeper. And so it's going to do the next set of 4 like this filters. But then there's also the prism that will be used. So this is a low resolution prism, but supernova are 10,000 kilometer per second explosions. So all of our lines are wide. And the prism, which has that nice wavelength coverage from 0.75 to 1.8, is really an effective bit. We're definitely looking at how to do that to optimize the transient science. Wide gets us out to a redshift of 2. Deep can go to 3. So that's one of the reasons as Masao was talking about different cadence choices. If you're focusing at the highest redshift, right, 1 plus 3 is 4, versus if you're at low redshift, 1 plus 1 is 2, then that's a factor of 2 difference in what your time dilation is going to be. So these are some of the things we're looking at. I'd say the optimistic statement is many different uses of this within the parameter space yield excellent cosmological constraints on cosmological parameters with on order 10,000 type 1a supernova going out to redshift ranges where we've barely gotten any supernova to date, and making those samples hundreds to thousands and really looking at where dark energy is starting to turn on. The coordination between Roman and Rubin is pretty important. The field of view is what it is, right? So for space, 20 square degrees would be an amazingly wide field of view, right? But still, as you run back to low redshift, you're still limited in that sample. And so the Rubin sample is very important for providing a well-calibrated low Z. And then out to a redshift about 0.7, there's a wonderful complement of having beautiful light curves all the way from optical to near infrared of 6 filters, perhaps 5, 6 filters of looking at the supernova properties, looking at the host galaxy properties, looking at the dust properties. So this will be such a key data set for that to really understand what's happening with type 1a supernova. One key principle that I think underlies so much, in particular I care about photometric calibration, but other calibration, is Roman and Rubin together are going to be the two of the best calibrated surveys. Euclid, to be fair, is leading the way here, of these next 10 years. And the joint efforts between those are going to be such a huge part of yielding the low systematics for type 1a supernova cosmology, as well as many others. If you're interested in learning more, you can read Ben Rose's paper, other papers in response to the community survey. Calls are relevant. Rebecca Hounsel had a paper earlier detailing the parameter space. There's lots of active effort to inform and help the cadence optimization. No, I get the word wrong. The community core definition survey team, it was just on the slide, I forgot, to give the tools to really figure out how to maximize the figure of merit for these stage 4 dark energy experiments. Thank you.
Oh, sorry. Okay. Hello, my name is Katarzyna. Can you hear me? My name is Katarzyna Kruszyńska, and I'm speaking on behalf of people who are interested in the Galactic Bulge Survey and also Galactic Plane Survey. So microlensing, Roman's main goal for Galactic Bulge Time Domain Survey is microlensing, which is in order to find exoplanets. But if we combine data sets coming from both Roman and Rubin, we can constrain our microlensing models better. Also, if we observe simultaneously from Earth and from space, we can find, we can constrain the mass of the lensing object. And that's with time domain information. The first thing which we can get out of just a single epoch is lens flux analysis, which is a very complicated thing. But in principle, we can constrain the blend coming from the light, which is very important in the galactic bulge. And this can be, well, this is one of the important products coming out of the galactic bulge survey, but it's also important if we just do one single epoch in galactic plane. This already gives microlensing a huge improvement for Rubin data. There's several more science cases we can get out of Roman and Rubin synergies. For example, astrometric time series, which is a complex topic in case of microlensing, but it gives us additional data set which would possibly lead to, for example, detection of compact lenses, for example, black holes. And there's like many more intricacies going into that topic. And I invite you to the Thursday morning microlensing session where Anibal Vara will talk in detail about how to optimize Roman and Rubin cadences for maximizing the scientific output. Additionally, coming in microlensing, there are two more things we can get with time series and or single epoch observations. First of all, if we have excellent Roman astrometry, we can predict microlensing events happening in an area where Gaia was not optimized for, which is an extremely crowded field, which can lead to amazing scientific discoveries. For example, I don't know, recently the predicted microlensing event was used to constrain model of white dwarfs. An additional thing, which is super important for microlensing, is microlensing optical depth, which is pretty much a probability that a star in a given direction is going to be microlensed. And if we get a single image from Roman and observations from Rubin, we can correct our observations for crowding, and that would be an amazing, extremely important result for us. There's also other examples that are that work both in the bulge and also galactic plane. It kind of depends whether or not we get one or more epoch in galactic plane. But there are airlines which needed to be corrected for extinction. They benefit from having like full SEDs observations like across the wide spectrum of wavelengths. There are cataclysmic variables which need SEDs. There's the galactic structure measurement, where you need to correct for crowding, for extinction and other things. And I invite you to basically to go to these 3 white papers. The most recent one was led by me, and it's about the galactic plane proposed survey. And I don't know, get excited about science products coming from Rubin and Rubin.
Okay, thank you. So thanks to the 3 speakers who spoke in their own words, representing the community voice on the motivation for having the Roman and Rubin synergy. So now Masao and I will talk about the current status from the community definition, the core community survey definition committees, and I'll start on the high latitude wide area survey. So I'm Keith Bechtol. I'm one of the representatives on this committee. If you look, you'll see probably several faces that you know from the Rubin science community. So we have good representation there. So I'll start by talking about the design reference mission. As a reminder, this was an existence proof that was used in the NASA planning of the mission to show that there would be an observing strategy that could accomplish the mission goals. This is not necessarily the survey that will actually be executed, right? So our job is to help optimize this, given all the latest information we have about the telescope performance and the science input from the community. So the nominal strategy was to have 2,000 square degrees to measure 10 to the 8 galaxy shapes and 10 to the 7 galaxy spectroscopic redshifts for cosmology. So this was imaging in 4 near-infrared bands spanning a range of wavelengths. It also, and in terms of how these observations would happen, to be 2 passes and 4 dithers. I'll show what that means on the next slide. 140 seconds per exposure. This also included GRISM slitless spectroscopy. So 4 passes and 2 dithers, 300 seconds per exposure. There's also a deep field of 20 square degrees that would go a few magnitudes deeper. So in terms of what this would look like as an example tiling, this would be one of the field of view for Roman with a wide area imager. You could do a tiling like this, and then one pass would basically building up area in a pattern like the following. And then there would be a second pass. And because of the constraints on the orientation of the focal plane relative to the sun, if you wanted to have the second pass at a different, if you want to do the second pass, you need to observe at a different time of year. So this is what the observations would look like. So we've, on the committee, we've been ingesting all the input from the community. And one of the big pieces of this that I want to highlight is that there seemed to be a push for having a wider area survey that would go beyond the nominal multi-band medium tier that we've been referring to in the deep tier. So we've been exploring that option. And I bring that up because it's probably most relevant for Rubin science. So the types of trade spaces that we're considering are summarized on this page. One of the things that I think is most critical for Rubin science is the selection of the filters. And one thing that I'll point out on the slide that Federica and Leanne spoke to, there's this wide filter, this F146, which has a much broader wavelength coverage. And so you could imagine using that filter if you specifically just wanted to cover as much area as possible. There are potential systematics with that. So let me just jump right to the big picture idea that we're considering. So again, the design reference mission considered 2,000 square degrees covered in 4 bands. We are at least discussing a 3-tier concept. We would reduce that medium tier to about 1,000 square degrees and then allocate the other half of the time to a wide tier and a larger deep tier. larger than the 20 square degrees in the design reference mission. I'll show a table with details in just a moment. So this is an example of the type of design that we've been talking about. So you'd have 30% of the total time allocated to the wide tier, 50% to the medium, and 20% to the deep. For the imaging, for the medium, it would be just like the design reference mission, so about 8 by 142nd exposures. For the wide area, you would limit that to a single band, for example, the H band, and then you'd be able to cover something like 4,000 square degrees, right, because of the increased survey speed. And then in the deep tier, we would expand from about 20 square degrees to 80 square degrees. And the idea is that you'd have this, these 3 different tiers that are each helping to calibrate each other so that you can control systematics based on the deeper information. And so the active topics that we're discussing, one of them is that if we were to consider this wideband, this W-band option, what would be the optimal exposure time to get the survey speed for the widest possible area? For cosmology, there's some systematics that we would need to consider. For example, you would want to make sure that you have dithers that sample the PSF robustly, so that you can do the weak lensing shape measurements. If you do consider this wideband, you have to make sure that you can control any kind of chromatic effects that would result from the stars and galaxies having different SEDs. And there's also the consideration of other cosmology surveys that are happening in the same area. For general astrophysics, we noted much of the input coming in from the white papers was stressing that having this really wide area, particularly overlapping with the LSST, benefits many different science cases in general astrophysics. And so there's some questions again about exactly the filter choice that optimizes that, as well as the timing if we were to do a second pass to get proper motion measurements. So with that, I'll hand it over to Masao. We are still open the pitch form, and you can send email for comments as well that we consider by the committee.
Okay, so I'll give a status update on the high latitude time domain survey committee work. So this is our committee. Brad Senko and I are the co-chairs of this committee, and we have a wide representation from people, experts on supernovae, AGN, other transients, spectroscopy, and so forth. We received 23 white papers and also 23 science pitches from the call. From a wide variety of science cases. Obviously, there were many white papers on non-1A supernovae, superluminous supernovae, kilonovae, pair instability supernovae, and other high Z transients, and the various strategies that will give us interesting science from those kinds of objects. We also received many white papers and science pitches on supermassive black holes, AGNs, what we can study with deep infrared imaging and also spectroscopy. There are also non-transient science pitches, including the deep galaxy surveys that we can do with these wide field imagers, high Z galaxies, and studying galaxy evolution. But there were also several white papers on interesting things that you can accomplish with combining Subaru, Roman, and also Rubin observations. So the main goal of the high latitude time domain survey is type 1A supernova cosmology. Here I'm showing 3 results that came out from the past 2 years or so. On the top left is the most recent one from the dark energy survey, supernova survey, the full 5-year sample that consists of about 1,800 type 1A supernovae. You can see the beautiful Hubble diagram. On the bottom left is a compilation made by David Rubin and collaborators called the Union 3 set that consists of 2,000 type 1A supernovae. And on the right is not a Hubble diagram, but it's a contour or sets of contours showing the constraints on WA and W naught from the Pantheon Plus sample that consists of 1,500 type 1A supernovae. The right plot and the bottom left plots overlap in data quite a bit, and they both come up with similar conclusions about the shape and size and location of the WA contours. So look at this Hubble depth on the bottom left, and you can see exactly where the data are sparse in this redshift region here, redshift above 1, and this is exactly where Roman can shine, and that's the main goal of the high latitude time domain survey. There are some constraints that were given to us. We were initially allocated 6 months of observing time over a 2-year duration, sometime in mid-mission, not at the very beginning, maybe starting in year 2 or year 3. We would like to observe in continuous viewing zones, so in the poles of the ecliptic plane, so that we can have continuous light curves of high redshift type 1a supernovae. We would also like to observe in low galactic extinction so that we are looking through as less junk as possible, as much as possible. The unique thing about Roman is that we can do imaging and spectroscopy. For the supernova survey, the better instrument to use is the PRISM spectrograph, where we get full field dispersion of the entire thing in the sky in the infrared, which is something that you really cannot do easily from the ground. So the supernova survey is trying to combine the capabilities in both imaging and spectroscopy to try to maximize the cosmology constraints from type 1a supernovae. This is just one reference survey, one example of several reference surveys that were published a couple of years. If you look at the top 2 rows that says imaging, wide and deep. So this particular reference survey uses 75% of the time on imaging and 25% of the time on spectroscopy. The wide portion will have roughly 19 square degrees, third column from the right, and the deep portion for the imaging will have 4.2 square degrees. And these filter choices and exposure times are selected to optimize the supernova 1a light curves at redshifts 1 and about redshift 1.7. Of course, these distributions are quite large, but these are sort of the target redshifts. And this is what you get if you use 75% imaging, 75% of the observing time on imaging. From the remaining 25% of the time, you can do PRISM spectroscopy and get redshifts of everything in the field, including the transient and also some of the host galaxies, but of a smaller area, 3.36 square degrees and 1.12 square degrees. So this is one of the reference surveys that was published a couple of years ago. You can invert the imaging and spectroscopy to 25% and 75% and try to match the areas covered by the imaging and the spectroscopic survey. So this is another combination of the observing strategy in which you get, in this case, the wide area will have 5.3 square degrees, the deep will have 1.7 square degrees, same areas for the PRISM observations, and you will get redshifts of every transient that you discover in the imaging data. And in the end, if you adopt this kind of strategy, we would end up with about 4,000 type 1a supernovae with excellent light curves in the infrared out to redshift about 2.5, with most objects having spectroscopic observations. So for redshifts and confirmation, and you can even do subtyping of these transients. But nothing has been decided yet. We are still trying to incorporate the white papers that would like to use spectroscopy for other things, trying to balance the imaging versus spectroscopy. Also, cadence is a big free parameter. For supernovae, we need something like a week. We can also accommodate something like 10 days, maybe even 2 weeks, if the redshifts are higher than 1. And so these are the kinds of things that we're discussing at the moment. In August, in late August, there will be a Roman community forum in which the High Latitude Time Domain Survey, the High Latitude Wide Area Survey, and the Galactic Bulge Time Domain Survey will present the next reference mission to the community, which everyone is welcome to zoom in, and we will update you on the progress, and then we will seek input again to do another round of fine tuning, and we'll go through that in October, and in November, hopefully write up the final report to the Roman project and the time allocation committee. So that's all I had. Thank you. Yeah, we're out of time. Okay, so let's move on to the simulations and data access.
Okay, thanks. Yeah, so I'm here to talk about the first topic here, the Rubin-Roman simulations. Before I begin, I'd like to thank the contributions of everyone on the Roman desk team who contributed to this effort, especially Michael Troxel, professor at Duke, who led the team and who provided the slides that I'm about to present. The Open Universe effort, or this simulations effort, actually came about as an unexpected opportunity that was presented to us by Katrin Heitman to use 2 weeks of uninterrupted dedicated time on the Theta cluster before it was set to be decommissioned at the end of 2023. And I just want to say first is that the Open Universe project is a directly funded NASA program which began in fiscal year 2020. And one of the goals of this is to use resources to provide cross-survey simulations and make the data publicly available so that researchers can use these data to develop their analysis algorithms and their analysis tools so that we can make the maximum scientific use of surveys like Rubin, Roman, and Euclid. And so with this opportunity to use these resources, we decided to put together an MEU combining the efforts from the Open Universe team, LSST desk, and the Roman project instrument teams to develop these simulations. So since we had collaborated, the desk had collaborated with the Roman team to produce coordinated simulations of the DC2 survey area, we decided, which mainly benefited static desk science, we decided to focus on time domain science for these simulations. And so there are 5 distinct goals for this project to satisfy that goal. So the first was we decided to focus on a deep drilling field within one of the LSST cadences, which shows the LISS-1 deep drilling field. And along with that, also have a Roman time domain survey, which is shifted to be coordinated and overlap the LIS region. We also wanted to use one of the most recent wide fast deep surveys, which included a rolling cadence in these simulations, and also have an overlapping wide area survey from Roman as well as a deep calibration region covering the same region. And so the simulated universe that we used for these simulations was the same as the one we used for DC2. However, this effort still provided us the opportunity to take advantage of significant improvements in the simulation effort since we did the DC2 simulation. And these consisted of improved modeling of galaxies and transients, as well as the software infrastructure which we used to produce the simulation. So on the software infrastructure side, the simulation, one of the infrastructure improvements the desk has been putting together is this package called Sky Catalog, which allowed us to define the input models for the simulations for the different instruments in a unified way to make it easier to run the simulations in the same way, both for the Roman and for the Rubin simulation. And this also entailed a bit of a rewrite for the Roman image simulation pipeline that Troxel put together for his DC2 simulation. On the transient side, we wanted to use the most recent models that the teams in desk and Roman had been working on. And this entailed making sure that the SEDs covered the needed wavelength ranges to cover both instruments, and also to make sure that the models could be incorporated in the Sky Catalog framework that I just discussed. And all the different types of objects that we had produced and put into the simulations are these various types of supernovae listed at the bottom there. One of the main improvements we wanted to include also was in the galaxy modeling over DC2. So part of the work that has been funded by the Open Universe effort has been a new galaxy simulation based on the Last Journey and body simulation. That was not ready or available for us to use for these simulations, but we were able to use the galaxy models with the Cosmo DC2 universe. And there's some thanks to Andrew Heron and Nick Kovacs and their collaborators on putting this together on short notice for the simulation. These entailed using self-consistent stellar population models in the bulge, disk, and star forming regions, and also entailed greatly improved realism in the SEDs to give us realistic colors and magnitudes across the entire Roman and Rubin wavelength ranges. And so the hope is that the improvements of these will lead to data sets which can be used to improve PhotoZ algorithms. And for the stars, we use the same GalFast-based star simulation that we do. So here are some plots of the galaxy colors as a function of redshift from the disk sky simulations in comparison to some Cosmos data. The points in green are the disk sky for the galaxy simulations, and the black points are the observation. So in the end, we were given 2 weeks, a 2-week period on the entire theta cluster after it had ended general use. This period unfortunately started on UTC December 31st, so that was New Year's Eve our time. So Troxel and I spent part of our New Year's Eve spinning up simulation jobs on this 4,000 node cluster, getting it near full capacity for nearly 9 days. And in the end, we used about 55 million CPRs to produce 4 million LSST and Roman numbers, or about 400 terabytes of data. And here's just a quick display of the status of the cluster a couple hours after it became available. And we had managed to get all 4,000, over 4,000 nodes running and generating nearly 250,000 images simultaneously. And we maintained that for the next 9 days, started to get the. So here's a summary of the simulations that we produced. Over 2.7 million images for the Rubin LSST simulations, and about 1.3 million for the Roman Space Telescope. Overall, 400 terabytes of data. Now, we prepared a small data preview data set, processing these data through the COAD stage, both in the Roman and Rubin data sets. And this covers about 0.5 square degrees, and you'll hear from Gregory Dubois-Felsman later on in the session about the availability of those data from the URSA website. And just to give you an idea what the Rubin simulations coverage was like, on the left here, I'm showing in blue the survey region. So that's approximately 25 square degrees for the deep drilling field. And overlaid on that is the sky map we used for those for the analysis of these simulations. And the preview data set is one of the small patches within track 2877. And that's near the very center of the simulation region. And on the right, I'm showing the number of visits per patch in each of the 6 LSST bands to give you some idea of what the depth of coverage is. And there's overall roughly about 2,000 visits per band. And so, as I said, we provided an initial data preview. If you go to this link here, you'll be able to see how to access those data. And eventually, once we finish processing all the data, all 400 terabytes will be released later this year. The image on the right over here is a multi-band image of the simulated Roman data with an inset zoom in on one of the galaxy clusters. And here's a comparison of a simulated image for that particular patch that we analyzed for the preview data set, showing the comparison between, on the left here, Rubin multicolor image and the Roman Space Telescope. So anyways, I'll stop there. Thanks. So I guess up is Axel. Okay. Axel, I can get the slides for you.
Okay. Hello, everyone. So I'm Axel Guino, and today I'm going to present our work to add Euclid-like images to the very nice simulation that we just seen. So I'm presenting this work on behalf of our team that worked on this. So I just mentioned that this work is done under the collaboration with Euclid, LSST, the Open Universe, and various group of Roman. So next slide, please. So, as I just mentioned, this work is based on the same simulation that has been used for the Rubin images that we just seen. And our goal is to provide same sky Euclid-like images public to everyone using the VIS bandpass. We will also provide only at the catalog level fluxes for the near infrared instruments, and all the tools that are used to make the simulation will also be made publicly available. So the goal is also to have this all those tools and images to the entire community, and this work is done jointly with the group of people that work on the Rubin simulation and also of the DDB. So one thing to note as well is that the simulations will not have the precision that will be required for Euclid science only, and so we are really tackling like joint processing for the simulations. Next slide, please. So our pipeline is derived from the Rubin MSIM code that was mainly developed by Michael Troxel, and that will be, I think, presented soon in a paper. So our code is hosted under the Gaussian developers. So as you see here, the code is still private, but it will be made public as soon as we can. Next slide, please. So one of the most important components of those simulations is having the PSF, the Euclid PSF, right? So for that, we worked with the Euclid Consortium, and we have to thank Lance Miller, who provided images in real space of the PSF. So this is not the exact Euclid PSF; it's a Euclid-like PSF, which will be good enough for the science that we are interested in with this project. And so we have, among the different things that we've done during this project, one of them was to slightly modify Gaussian to allow us to use this kind of objects and create directly interpolated chromatic objects. Next slide, please. So to simulate very bright objects, so the PSF that were provided is very good for all the galaxies and stars that we use for science. But for very bright objects, we have noticed some artifacts. And so for that, we used a slightly different model for that only concern extremely bright objects, so to have like better looking images that includes, for example, the diffraction spikes that we would expect. And so for that, we used a Euclid-like pupil plane to make this sorts of PSFs. Next slide, please. So at the moment, the simulation includes various effects. So for the zodiacal light, we use a very similar code as the one used for the Roman MSIM simulations. We also include the read noise and exposure time from Euclid, and the bandpass and charge diffusions were provided through the PSF. So in the future work, we also plan to add more effects, like for example, the stray light. Next slide, please. So another very important part is the observation sequence. So for that, we use the Euclid planned observations. So like that, we can get right the dithering pattern and also the Euclid coverage. Also, one issue of this, so it has been mentioned that the current simulation includes transients. And so at the moment, we don't really have time overlap with the simulated catalog, but that means that at the moment, we don't have the transients. So it's something that we are currently working on, and we'll do our best to be able to include that and so enable science also for like time domain science. Next slide, please. So here we have our first image that we have simulated. So this is a Euclid-like focal plane. And if you go to the next slides, and here is some very preliminary coad. So we have simulated single exposure in the same field that has been recently released for Rubin and Rubin, and made a coad for the Euclid-like images that we have simulated to be able to make some comparison. And if you go to the next slides. And so here we can see the comparison between Euclid and Rubin, which I think very highlights the interest of having a joint processing of these images, where LSST will be deeper than Euclid, but Euclid has better resolution. And so different kind of objects will appear on both images, and like we will, having the joint processing will really, I think, enable a lot of science from those two collaborations. Next slide, please. And so here, just as a summary, so we have the machinery to make realistic Euclid-like these images. We are working to make the catalog level near-infrared simulation. And the big important component is that it's on the same sky as the simulated Roman and Rubin images. So our PSF, we believe, is good enough for a lot of things. So if we want to study joint detection, the blending, photometry, and galaxy morphology, and I'm pretty sure many other science will be made available with the simulations. And so, as I mentioned in introduction, all the codes associated to like making the simulation will be made public. So if there is anything that people think it is important, it's something that we can implement, or people can implement themselves if they prefer. So at the moment, the code is private, but will be made public, and we believe that all those images will be also made public by the end of the year. So in the future, we're planning to add more instrumental effects to make the simulation closer to the Euclid images. And we are also planning, on top of making the single exposures, to also simulate the co-added images. And that's it for me. Thank you.
Hey, guys. Okay, next up is Gregory.
Thank you very much. So as I think was already mentioned, the NASA Open Universe project, coordinated by Alina Kiesling at JPL, has sponsored hosting these coordinated Roman and Rubin simulations that you've heard about here in the Amazon Open Data Repository. The NASA Infrared Science Archive, URSA, is providing the technical support for the deployment of this data. And so far, this preview release has been made available. So there are links here in the slides for later to the release announcement and to the URSA data access page. So I just want to say a few things about this quickly. So this is just an image of the homepage for the simulations at URSA. There are notebook-based tutorials available. Those are shown here on the right. So it's just as an example, and there's a link to them. Oops, up there. This will be extended as the project continues when the full data set is made available. And right now there are only tutorials for the Roman data. We'll be adding tutorials for the Rubin data on the URSA page as well. Just want to mention, for those of you who want to start working with this, there's a little caveat on the Rubin data. We just discovered, basically over the weekend, that for a subset of the Rubin single epoch image data, there were 2 processings of images that were included in the data provided and released. It was an artifact because there were some of the original processings partially failed and had to be rerun, and both the first and second versions were, if you're familiar with the Rubin middleware, in the Butler repository, and the whole repository was exported. So if you're using a Butler to access it, you don't notice this because the Butler takes care of superseding things, but it was revealed when doing the export. So we're starting to work on a recipe for downloading a deduplicated version of the data, and we will also look into removing the superseded files altogether from the cloud service. And then I just want to make a little advertisement for some future work. Right now, the data are available just through the S3 interface. and through HTTPS URLs, because it's in the open data repository. You don't need to use S3 API. You can use HTTP to get access to the files. But we would like to provide a Butler interface as well over the data, and we've demonstrated this internally. We are stretching the Butler in a direction that it hasn't been used yet, so we found some scaling and multi-user access issues that are associated with making this available more widely, so we're not ready to announce that yet. And some of this is tied to features of the Butler that are still being worked on for the Rubin operations era. We're evaluating providing a read-only Butler interface as an interim step. I think that's all I had to say about this. Yes. So are there any questions about the data access? All right. What's next?
Okay, so I understand that the group photo is at 5:30, which is pretty soon. We have just a few minutes if there's any questions on we were kind of rushing through because we wanted to make sure that we finished on time, but if we have just a few minutes if there's a question from any of the talks. Yep, this one here.
I'm Pat McCarthy, the director of NORLab. I don't have a question, but more of a comment. A couple of comments. First, this was a fantastic session, really interesting talks. But the bigger comment is I have never seen this level of coordination between the ground and space before. I think this is a remarkable change. I think it's the case that all of the missions are already mature, no one's at risk, but every mission benefits by us working together. This is a really quite a change in astronomy and astrophysics. I want to say on behalf of NORLab, the group that will operate Rubin, we're really committed to this. We think the scientific potential is huge. We haven't talked yet about how much it's going to cost, how we're going to do this, but let's not let money get in the way of such great science. So I just want to say that this is a fabulous opportunity. We'll support it fully. And thanks everyone for all the work that's been done. It's clear people all around the world want to make this happen. We're fully committed as well.
Yeah, I would second that comment. So the great hope is that we will discover the unexpected. And most likely that's going to happen in the faint time domain. There's a whole unexplored region in the faint time domain on the in around something like 1 day, plus or minus a factor of 10. Unexplored completely. But to do that, we're going to have to observe the same piece of the sky simultaneously with these surveys. So that's a thought to consider if you can arrange that. That's easily done, I think, in the deep drilling fields.
Very much agree with that. And also the key to understanding those weird objects is, I think, spectroscopy. Right.
Thanks, Tony. Any other questions before we wrap up or comments?
Can we ask a question from Zoom?
Yeah, please go ahead.
Hi, thank you for these very interesting talks. And I'm wondering for the Euclid-Rubin DDP production, there have been 35 expressions of interest, and our team was among those. And for requesting for funding to perform this analysis, the first proposal started this fall. So I was wondering when the proposals will be organized and we will know if the single teams will participate to the effort and how, what will be the role of each team.
I can say that we are aware that there's proposal time in the fall. We are still analyzing the community survey stuff we got. We basically should have overall, basically in August, we should break down exactly what we have gotten. And then, so we're hoping kind of September-ish, October, which of course pushes right up against these things. But we're going to do our best to try to give some feedback that could be helpful for proposals. But the timing is not quite working out perfectly, but we're going to do our best.
Yeah, it will be good to have an endorsement to the group proposals for funding, but that should be happened before. And if you would like to have the European groups to submit for their proposals, so before October, if September is possible, that will be more inclusive towards European groups.
Okay, maybe time for one more question, remote or in the room. All right, once, going twice. All right. Thank you again to all the speakers for a great session. And enjoy the photo.